Bonjour à tous. Donc aujourd'hui, on reçoit Anaïs Berthereau qui, si je ne me trompe pas, est en dernière année de thèse. C'est bien ça?
Oui, oui, c'est ça.
Et je ne sais pas si tu vas nous parler d'ondes gravitationnelles, mais en tout cas, tu vas nous parler de pulsars, de chronométrie des pulsars, et puis surtout des choses plus embêtantes qui sont les RFI et comment se débarrasser de ça. Merci, je te laisse la parole.
Merci à toi. So, hello everybody. So, as Philippe said, I'm a third year PhD student. I'm working in Orléans. And today I will talk about my work about using deep learning to detect radio frequency interference in pulsar observation. So I will first talk a little bit about pulsar, how we study them, and why we need to remove interference in our observation. I will then present two different methods for cleaning observation, and then we present our result for our method. So first of all, what is a pulsar? A pulsar is a collapsed core of a massive star that was at least 8 solar mass. This is a dense object. The radius is roughly 15 kilometers for almost 1 to 2 solar mass. It's a highly magnetized core. Above each magnetic pole, there is a radio beam. And once the magnetic axis is not aligned with the spin axis, the beam sweeps through the space the same way that a lighthouse does. So when we are observing a pulsar, when the radio beam crosses our line of sight of our telescope, we will then see a pulse. This is what you can see on my slide. This is the profile of a pulsar called 1909, observed in the Nancy Radio Telescope at the frequency of 1.4 gigahertz. And this is the kind of pulse that we can see when we are observing pulsar. This is a profile, so this is a signature of the pulsar. Each pulsar has its own profile. You can have two peaks, you can have a thinner profile or everything else, but this is a pulsar profile for 1909. And we can see this pulse every time the star is rotating. Thus, the pulse period is directly related to the star rotation. And we can then distinguish two different populations for the pulsar. One type that we call the millisecond pulsar, which period is under 15 milliseconds, and the non-millisecond pulsar, which period is above. So here you have the PP dot diagram. So you have the period in one axis and the first derivative of the period in the other one. And you can see the two different populations. The millisecond pulsar is in dark blue. And it's important to take the period of the pulsar in consideration when you are observing it, because it will affect the way that you are, the kind of, the way that you are folding the observation when you are observing the pulsar, because you're observing the pulse every time the star is rotating, so the period has to be taken into account when you're observing your stars, if you want to see every pulse that you can. And the way that we are studying pulsar is what we call the timing. So we are measuring the time of arrival of the pulsar, a TOA. And this TOA is measured by cross-correlating the observed pulse with a reference profile for the pulsar. So we are making a template of this profile by averaging the best observation of the pulsar. So we have the best SNR pulsar observation. So we have then a template that we will cross-correlate with every observation that we have to get a delay in the phase, a delay in the time domain. And the TOA will then correspond to the time that we started the observation plus this delay with observed pulsar. Then when you have this TOA, that corresponds to the times that we have received the pulse, we can go to the emission time in the pulsar co-moving frame by applying some correction to the TOA. So this correction corresponds to some delay from the propagation of the signal through the solar system and through the interstellar medium. And sometimes we had a binary correction because when you have a companion with the pulsar, you can have some relativistic effects that you have to take into account when you want to make something very precise. So this is the three terms that we are using for our corrections to go to the emission time in the pulsar frame. With this time, we can modelize the rotational phase, and we will then, with this modelization, try to find the best parameter that will describe the pulsar and its environment. So these parameters are included into the correction terms that I showed you just before. And we feed this model to the data. We will have what we call residual. So this is the difference between the model and the observation. And our goal is to have the smallest residual possible, so that we mean our model will correctly describe the pulsar and its environment. And here you have the result for 1909. So this is the timing residual for this pulsar. And as you can see, the pulsar are very close to 0. There is a range of 5 microseconds. So this is a good timing for the pulsar. And as I said, we are trying to do the best observation possible because our main is to have the most precise measurement for the most precise measurement for the TOA, so we need very good observation. At the NASA Radio Telescope, we're observing in radio in the range, frequency range from 1.2 to 3.5 gigahertz. And here you have the spectrum in France for this frequency range. And as you can see, this is kind of crowded. There is a lot of other applications for this frequency, so we are not alone. And one of the results is we have a lot of perturbing signals in our observation that we are calling the radio frequency interference, RFI, that we need to identify and remove because we are observing pulsar and not human signals. So another reason is that even if we don't have a lot of RFI, we need to remove them because TOA are noise dependent. So as you can see in the equation 5, the uncertainty of the TOA is directly dependent of the ratio with the SNR. But it is not the most problematic things because here you have an observation of a pulsar, still 1909, because this is our best pulsar. It will be the start of my presentation. And you have an observation, you have a frequency phase diagram here, and just under you have the flux of the pulsar. You cannot see the pulsar in this observation because you have a very strong RFI, the horizontal line. And the pulsar is hidden behind this RFI. If we could see a pulsar in this observation, you would have a vertical line. So the RFI are problematic because first they are we can miss the pulsar behind them. And secondly, even if they are not strong to hide the pulsar, our TOA are totally dependent of the noise. So we need to remove them. For this purpose, we have two methods. The Coast Guard, that is our standard method that is based on statistical computation. And then I will present you the deep learning methods that have been developed for the past month. So for Coast Guard, what we are doing, we are using the pulsar observation that which are 4-dimensional array. So you have a dimension for the polarization, one for the frequency channel, one for the sub-integration, and one for the pins. Except for the sub-integration, every other dimension are statics. We have the same number for every observation. And the sub-integration with number of the sub-integration will vary depending on how many sub-integration we have during a 1 hour observation. And this will depend from if the pulsar is an MSP or not. It depends to the pulsar period. So what Coast Guard is doing, it will subtract the pulse signal from the observation as a first step. And then from this observation, it will statistically analyze the resulting dynamic spectrogram. So it will make a spectrogram. So this is a time frequency images of the observations that you have here. And from this image, it will compute some statistical values such as the Fourier transformation, the median, the standard deviation, or even the median absolute deviation. And from this value, it will apply a threshold to determine if it's an RFI or not. So if you're above the threshold, you are considered as an RFI. And then it will create a binary mask of the RFI, and this for each observation. So when you apply the Coast Guard mask for this observation that you have here on the right top, you can have the clean observation here. So now you can see the pulsar. You can see the pulse at 0.4 in phase, and you can see the vertical line that I was talking about in the same phase. So now you can see the pulsar, and you can do the TOA and the studies that we made. For our methods that we are developing, because one point that I did not talk about is that Coast Guard is great. This is a very great method, but sometimes it removes signals that we are not very happy, because we need most of the signals since we want to study the pulsar. We need to have the pulsar signals. So we are trying to find a way to make another method that will remove the RFI, but keep most of the signal. So this is why I have been developed the deep learning method that I will present you now. So for this part, what I'm doing is a particular type of image classification that we call the image segmentation. The image classification is when you label an entire image with, for example, cat when you have a cat pictures, or boat when you have a boat picture. The image segmentation is a particular type because you're not giving a label to the entire image, but you're giving a label to each pixel. This is what you have in the example. So you have an input image of a car on the road, and you have as an output some label for different group of pixels on the image. So you have the vehicle in orange or the road in blue. For this purpose, we are using convolution layers because it's a great tool for feature extraction. The convolution can achieve pattern recognition to classify the pixel groups. And the architecture that we are using is the unit. So if I've correctly remember, someone already presented this architecture, but this is the unit we are using, and it's called that way because it's a shape of a U. You have a down stack part and an up stack part. The down stack extract important feature that will describe the image and the label. And this will be done through convolution layers. We will have then at the bottom of the U a features vector. And from this features vector, we will reconstruct an image with a label through a transpose convolution layers. And this is the upstack. For our network, we are only training the upstack because for the downstack, we are using a pre-trained encoder from TensorFlow, mobile video, and this is a very great encoder because it's light, it's fast, and has great result for encoding data. So we are using the property of the transfer learning. That means that we are using a network that has been already trained for another task, but we are using for our task, our own task that is extra important feature in our radio observation. At the end, as an output, we will have a binary mask reconstructed by this network. So our data set is the same that for Coast Guard. We are using non-cell radio observation. That has still the same dimensions that for the Coast Guard that I present you. So we still have a four dimension, and we will make a reduction in the bins dimension by computing three different images. The first one will be median of the bins. The second one will be the median absolute deviation, and the third one will be the peak-to-peak. So the peak-to-peak is to measure the difference between the maximum peak and the minimum one. And these three images are in the frequency and temporal frequency time domain. So this is still dynamic spectrum, but this is the median dynamic spectrum, the mad dynamic spectrum, and the peak-to-peak dynamic spectrum. So these three images will be considered as a one input with three channels because it is our network input shape. The pre-trained TensorFlow is optimal with a three channel input. So we want to take advantage of this. And as a ground truth label, we are using Coast Guard mask. So this two entries will be our input for the learning process. Our dataset is composed with 37,000 observations from 1.2 to 3.5 gigahertz. 60% of it are millisecond pulsar observation, and almost 80% are observation at 1.4 gigahertz. So I've been working on this project for a few months, and I could see some problem emerging time to time. One of them was that during our previous attempt, we had issue with strong RFI. This was small, but very strong RFI that was periodically located in the dynamic spectrum. We tried to imagine two different solutions to improve the detection of this RFI. First one was adding weight to the classes to help imbalance data. So our classes are, for each pixel, basically just RFI or not RFI. And for the Coast Guard maps that we have passed to the network, we saw that for in an average, 30% of the mask is only RFI. So our network was smart but lazy. And for it was a better guess to just flag something as not a RFI than a RFI. So to help this, we add weight to make RFI more important during the learning process. We then tried to make RFIs that were similar to those which were not well identified. So we generated them with some procedural script. This is an example that you have. So you have the dynamic spectrum that will be passed to the network and the procedural generated mask associated. We make sure to have some background noise and the same noise levels from our true data set. And we included this to our data set for the learning part. From these two options, we had then four different configurations. We have a network with no weight and no generated RFI, a network with weight, a network with generated RFI but no weight, and a network with generated RFI and weight. We tested these four different configurations. And we measure some metrics to help our decision. We measured the precision and the recall. So the recall is the part of correctly identified RFI among the actual RFI that describe the false negative. And the precision is the fraction of correct identified RFI in the entire RFI class. So that we measure the false positive. In a simpler way, the greater the precision is, the lesser you will identify signal as RFI. And the greater the recall is, the lesser RFI is identified as not a RFI. For our problem, on the first step, we don't want to miss an RFI. So it seems pretty okay for us to flag signal as a RFI on the first step, because we really don't want to have RFI in our observation. So we will use the best recall score. So that was for the configuration with weight and generated RFI but no weight. And from these two different configurations, we then check the signal noise ratio for some pulsar and at different observation time dates. So as you can see here on the plot with the signal noise ratio, the weight configuration only is represented by green circle, and the generated RFI but no weight is represented with pink star. And you can see that the green circle is almost every time above the pink star. So we decided to take this as our final design. And we then don't use the generated RFI, but we use weight during the learning process. So this is our method of the deep learning. And now I will present you some results, what we had from applying this method to our observation. And first is the cleaning observation. So I remember that we started from this observation in 1909, that we couldn't see any pulse. And you have the result of the cleaned observation, just under. So we will see if our pulsar is either seen with our method. And as you can see, we have some trouble with this pulsar and this observation. So you have on the left, the 1909 cleaned by Coast Guard, and on the right, an observation of 1909 cleaned by our deep learning method. So we have, you can see the pulsar. So this is an improvement from the raw observation, but you still have some RFI that you clearly can see on the profile plot that you have some noise on the baseline. And this is RFI that you can strongly see here. And as a result of that, the signal noise ratio is not so great for the deep learning method. We are way under than the Coast Guard method for this observation. I will then talk about another pulsar, 1528, which is different from 1909 because 1909, I'm sorry, I didn't say it, but 1909 is a millisecond pulsar with almost 3 millisecond period. And this pulsar, on the contrary, is not a millisecond pulsar with a 50 millisecond period. So this is a different kind of pulsar. And here we are cleaning quite, it's not that bad, not as 1909, but there's still some trouble with the strong RFI that you can see on the top of the frequency pulse phases plot. And so this is still the same trouble. You have a baseline that is that contain sinusoidal noise. And this kind of noise is problematic because when you are doing the cross-correlating in the frequency, in the phase domain that we are using for the TOA, you need to have the cleanest pulse possible, and this little sinusoidal noise are giving us some trouble to the TOA actually. But this is a clean observation result. And what I'm saying is that that may influence the way that we are making TOA, but we need to confirm that hypothesis. So we studied the impact of our method on the TOAs. And for that, we are using 1 year of observation from the 1st of January of 2020 to December. We are using 6 pulsar observed for the European Pulsar Timing Array project. So the EPTA project is using pulsar with the chronometry with the timing method, so the TOA method, to detect gravitational wave using the pulsar as a network of detectors for the galaxy. And we are using also 3 MSP pulsars. So the 6 EPTA pulsars that are shown here are great pulsars that are observed for a long time, and we have a lot of observation for them. We then have the 3 MSP pulsars that have been chosen because they are the most observed pulsars that are not MSP in NANSE. So you have 1528 with 60 milliseconds, and then you have 0248 with 200 milliseconds, and the slowest is 1136 with 1 second. So we have our 2 population of pulsar for the test, and our goal is to analyze the impact of the network when you are cleaning the observation with this method, how it will affect the TOA depending on if it's MSP or not an MSP, because as I said, the RFI are different for the period that we are for the pulsar, because it will depend the way we are observing it. So here you have the results of this analysis. This is a plot with the signal noise ratio for the new method and the signal noise ratio for Coast Guard. And you have on the other axis the new uncertainty and the new uncertainty, and the Coast Guard uncertainties. So to have a better idea of how to see these plots, the base configuration, the one that means that we have a better uncertainties with our network and a better SNR. This configuration means that we should have more points on the right bottom of each plot. So as you can see, this is not the case, but most of the points are in the center of each plot. So that means that we are doing at least as good as Coast Guard. This is not a bad news. We also see that even if we don't not doing better than Coast Guard in many cases, there are still some cases that we are doing great, a better job than this method. So it's in a sense great. To be more precise, for 1909, that you can see is that we are better than Coast Guard in 30% of the theories that we are making from the cleaned observation. And for 1528, it's only 7%. But we cannot see, as you can see here, that we can not conclude if we are doing a better job on MSP or not. It seems that we cannot conclude from this part from now. So I will conclude, sorry, for this part and for the talk. For the past month, we improved our method, but we still have the same problem with the strong and periodic RFI. We have difficulties to identify them and then remove them. The theory that we are making from this cleaned observation seems badly impact. The uncertainties are greater for most of the observation. And we think that is because we are using Coast Guard mask as a ground truth label, because our network is using this mask to learn how to detect RFI, so it can at its best do as good as Coast Guard. So we are thinking that is the limits, and to go to pass this limit, what we can do is training the network with simulated RFIs with the associated mask, or a mix of simulated RFI and true observation. Because we could have the ground truth label will be the ground truth label, depending on another method that has its own flaws. So that will be a solution. Or we could use generative adversarial network that has another kind of network that is in fact true network. That are in competition, you have a generative part that will generate RFI, and you will have a discriminator part that will have that will try to say if it's an RFI or not. So they will be in competition, and they will learn together. And then at the end, you have a generator when you need to generate RFI, and then you have the discriminator when you can discriminate the RFI. So that could be some solution. But we also have another alternative that we are working on, an alternative to the segmentation image methods, a baseline noise analysis. So this method, for each bin's sub-integration and frequency channel of the observation, will subtract the pulsar signal, to only keep what we are assuming is noise. So this one dimension signal that we are supposing is only noise will be passed to a boosted decision trees. algorithm. And as output, you will have the probability that this signal is only white noise or an RFI. You will apply then a threshold to determine if it's the RFI of the white noise, and then you can classify this part of the observation. If a band is classified as an RFI, the entire sub-integration and channel associated with this band will be flagged as an RFI. So then we will have at the end a binary mask of 2 dimensions with the number of sub-integration and the frequency channel, the same way that we had with Coastguard and the deep learning method. We have some results for this measure, preliminary result, made by Luca Guillemot. And so they still have the 2 pulsars that we were talking about previously, 1909 and 1528. And so the method has been run from more than 1 year of observation. So that's why you have a more lot of delay. And as you can see here, the results are great because there's more print on the bottom right of the plot. That means that the method is doing better than Coastguard. Almost 50% for 1909 and 40% for the other pulsar. And most of the points are in the center. So this method seems to be a great improvement. The only problem is that since we are doing the computation for each band sub-integration and frequency channel of the observation, that means a lot of computation. This method is slow, so we are trying now to make it faster by running it on GPU. And to make it more competitive with Coastguard, which is faster than this method for now. So thank you for your attention, and if you have any question.
Thank you. So do we have questions? I have one question about what you said at the end about the time computation. How fast is the computation? I mean, how do you compare the 2 methods between Coast and the machine learning method? Is the second one much faster?
Between the machine learning and this method? Or
the very first one?
Coastguard, I don't have any information about how time make Coastguard to compute, because the masks are done during the processing pipeline. So I already have the mask when I'm trying to work. But when I'm running Coastguard on different observation to test things, what I can say is that Coastguard can take a few seconds for very big observations. So, for example, 1909 has a lot of sub-integration. It can go to 900, so that make very big observation. And then you can have 1 or 2 seconds to use Coastguard on it when the deep learning is faster for that. I don't have exactly the difference between them, but when I'm running the deep learning method, I usually make it for a batch of observation, and it's clearly faster than Coastguard. But then we have flaws. We cannot detect every RFI, then we have some trouble with some RFI. So maybe I'm faster, but there's still RFI at the end. So this is not, well, there are compromise.
Yeah, yes, but there is room for improvement. And if you're faster, then it makes sense, because if you want then to go toward real-time calibration, then it's useful to test those kind of methods if they are faster.
Yeah.
Any other questions? Aurélien.
Yes, thanks for the talk. So it was just to know this new method, the the fact that it has better performance, it's due to this big RFI that it arrives to find, or it's something else?
This method from Luca's work. Well, what we are thinking is that since we are working on each bin sub-8 and frequency channel, where for my method and Coast Guard, we usually make statistical, we compute statistical value through the bin dimension. Since we are using every part of the observation to determine if it's an RFI or white noise, you are very more precise, in fact, because you're going through each part of the observation and you try to identify if it's white noise or RFI. So you're not working on an average observation. You see what I mean?
Okay, yeah.
Je pense qu'ils en sont aux questions.
Absolument, nous en sommes aux questions.
Exactement.
Est-ce que quelqu'un a d'autres questions? Non? Je propose qu'on s'arrête là du coup. Merci encore pour ce talk, Anaïs. Et puis, je vous dis donc à la semaine prochaine pour le prochain talk de Minerva. Merci beaucoup.
Merci.